So today we're going to talk about arc length. What does arc length mean? All that arc length is the length of a curve. So if I were to have this curve right here, what's the length from this endpoint to this endpoint? So calculus allows us to do a really cool method of finding arc length, but to start, let's say I didn't know that. One method of finding arc length would be to tape a string from the end, maybe tape it at various points throughout so that I would have a generally accurate length that's following the curve. And then I could take the string and stretch it out against a ruler to see how long the string is, and that would be the length of our arc length. Well, that doesn't always work so well when you start to get complicated curves, or maybe you just don't have string. So there has to be another way of figuring it out. So one way of doing it is to break up your curve into itty bitty pieces. So I'm just going to take this curve and break it into several pieces. And then I can call each of these little pieces maybe line segments. Okay, now I know that the curve itself would have a curve to it, but let's say I'm just estimating each of these segments or pieces by using little line segments. So let's call maybe one of the line segments right here from this point to this point. Let's call that line segment delta S. So I'd have a lot of little line segments to add up. So we'll call all these little pieces those little mini delta S's. And so basically my arc length would be the sum of all those little delta S's. So just like you broke when you were finding area under a curve, just like you broke that area into rectangles, or when we were doing volume, we broke the volume into disks. We're going to break this distance here into little segments. So because this is curved and I don't know what that actual distance is, we're going to estimate it with a line segment. But let's say I'm not sure how long that line segment is. I can drop a vertical and a horizontal and maybe get these two distances to help me figure out what this distance is. So my vertical distance, because we're going up and down, let's call it delta y, and my horizontal distance would be delta x. We can use these to help us figure out that line segment length. So what does this look like? Well, this certainly looks like a right triangle to me, or what should be a right triangle, right? And so when we have right triangles, I start to think of the Pythagorean theorem. So I start to think, okay, well, my hypotenuse squared is equal to the two side lengths squared. So I'm starting with that. Okay, well, I'm not really worried about what delta S squared is. I want to know what delta S is. I want to know what that segment's length is. So how can I get rid of that square? Well, we would take the square root, right? Because the opposite there is the square root. So I'm going to take the square root, and I would end up with the square root of delta x squared plus delta y squared. Okay, so let's start to think a little bit. Well, using some algebraic manipulation, we know that if I divide by something and multiply by that something, I'm really not changing anything. I'm just manipulating it, and I'm really just working with a form of the number 1, right? So let's say I divide, so here's my delta S again. Let's say I'm inside the radical, and I have my delta x squared plus my delta y squared. And let's say I divide that by delta x. squared. And still inside the radical, I multiply by delta x squared. Notice, am I really changing anything? No, because multiplying and dividing by the same number is really just multiplying by the number 1 or working with the number of 1. So you're not really changing anything, but it certainly allows me to manipulate things a little bit. Using the idea of the square roots of a product, when I have something inside a square root multiplying something else, I can take the square root of those two separately. So that's what I'm going to do next. So now I have the square root of x squared plus delta y squared. I think I said square root of x, delta x squared plus delta y squared, all over delta x squared times the square root of delta x squared. Now, we can, of course, simplify this. There's a lot of things to simplify here. First of all, this first piece, delta x squared divided by delta x squared, would become a 1. I can write delta y squared over delta y squared. And, of course, this part on the right will just become a delta x. So let's simplify that. And you know what? I think I'm going to take this delta y over delta x and actually put the square on the outside. So using some of our power rules there. Okay, so what have we here? This is the distance for our little line segment, and it is equal to the square root of 1 plus delta y over delta x squared times delta x. So let's scroll back up for a minute. Let's say we weren't just dealing with this number of points on the curve. Let's say we were dealing with a lot of points. So let's say our points are increasing. As our points on the curve are increasing, that means our delta x is approaching 0 because the distance horizontally between one point and the next is becoming less and less and less. And that certainly sounds like a concept that we talked about in Calc 1, or that you would have learned in Calc 1. And that's basically the idea that as the limit as delta x approaches 0 of your vertical and horizontal distance, you get what's called the derivative. That's pretty much the general idea of a derivative. So if I scroll back down here for a minute, and I think to myself, well, what happens if the number of points on this situation increases and goes to 0? Then my delta x would be approaching 0 in this. And I would end up with the idea that we're working with derivatives. So we would have ds is equal to, and then all of these delta y and delta x's would become the dy and dx terms. So 1 plus, using that idea of the definition of the derivative you learned in Calc 1. So here we go. And then as we sum all of those up, all of these pieces together, we would end up with the idea of the integral. And the integral would be the addition of all those line segments as the number of points increase. And this is the definition for the arc length. So going back to our notes, that's generally what we're going to do when we are finding the definition of the arc length. We are going to use that little formula that we just kind of talked our way through a little bit. It wasn't totally formalized, but the general idea is there. We're going to be taking the antiderivative from a to b of the square root of 1 plus the derivative squared. And this can be done in terms of x or y. If it's in terms of y, it'd be a dy on the end. The derivative would be in terms of y, and your a and b value would be in terms of y. Okay, so let's see what an example of this looks like. So for example 1, it says we need to find the length of the arc of this semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. So to start, I kind of want to see what this would generally look like. So if I were to draw a quick sketch of what it is that I'm working with here, we would actually be graphing the function y equals plus minus. So you'd want to do a positive and a negative version. So here's our positive, here's our negative, okay? And so we're talking about the portion from 1, 1, so let's say 1, 1 is here, to let's say 4, 8 is up here. Okay, so we're talking about this curve. I want to know the length of that curve. So first of all, we need to remember our formula here. I'm going to need to work with the derivative of this function. So let's figure out what that derivative is. So we have, to start, y squared is equal to x cubed. And since I'm working in that top quadrant, I'm only really going to need to worry about the positive version of this. Whoops, x cubed. Whoops. And so now we're just going to worry about that positive version. So the square root of x cubed. Okay, so that can be rewritten just to make the derivative a little easier as x to the 3/2. Okay, so now let's calculate that derivative. So I like to calculate the derivative before so that I'm not having to do a lot of calculation once I get into the integral setup. So the derivative of this is 3/2 x to the 1/2. So we are ready to go. So we are going to take this function and figure out the length. Now, because we're dealing with this in terms of x, we're going to use the x values from the points. So that's going to be from 1 to 4 for our upper and lower bounds. And then we can go ahead and put in 1 plus, and then our derivative, and a dx on the end. And now all we have to do is simplify this and start finding the derivative. So this would simplify, or start finding the integral. So this would simplify, of course, we get the square root of 1 plus 9/4 x. The 3 squared is 9, the 2 squared is 4, and the x to the 1/2 squared is just an x. So this is ready to roll, and then we can actually use a u substitution on this to take the antiderivative. So the u is going to be the inside, and du in this case is going to be 9/4 dx, and that means we're going to have 4/9 du once we solve for our dx, and now we can start replacing things in our integral here. So let's go ahead and do that. We'll do our u substitution here. When I'm doing it in terms of u, I'm just going to drop the bounds until I bring it back in terms of x, because these bounds are currently in terms of x, and I'm currently writing my integral in terms of u. So that 4/9 I'm going to put out in front, and then I'll write that as u to the 1/2 du. Again, it would be u to the 1/2 because this entire piece in here is now u, and the square root, another way of writing that, is to the 1/2. Okay, so now I'm going to take the antiderivative there. So I'm going to get 4/9 times 2/3 u to the 3/2. So you're adding 1 and dividing by that new exponent. So that's really, in this case, multiplying by 2/3. So we would end up with 8/27 u, I forgot my 3 there, or excuse, yeah, my 3, to the 3/2. Okay, now let's put it back in terms of x that I can then evaluate using my bounds. So that 8/27 is in front there, and I would have 1 plus 9/4 x, and that's to the 3/2 power, and we are evaluating at the numbers 1 and 4. Okay, so let's see if we can start to simplify this a little bit. So we would end up with 8 over 27 times, and if we were to plug a 4 in there, that would be 10 to the 3/2 power. If we were to plug a 1 in there, I believe that would be a 13 over 4 to the 3/2 power. So I just kind of got a little common denominator there when I plugged 1 plus 9/4 together, or when I added 1 plus 9/4 together. Okay, so I can actually, change the way this is. Remember that 10 to the 3/2 really means 10 cubed squared. So really we have a perfect square of a 10 in there, and we have 1 left over. So that's kind of how I'm gonna rewrite this. So we have 8 over 27 in front, and I'm going to write that as 10 root 10, and I can write that as plus, and I can do the same thing for this one, 13 over 4 root 13 over root 4. Just kind of simplifying that down a little bit. Well, root 4 obviously simplifies a little bit, right? Because root 4 is 2. So we're just doing some simplification, making it look nice. And we always love to make it look nice. So we have 13 root 13 over 4 times, and this root 4 is now 2. So 4 times 2 is 8, right? So now we have an 8 in the denominator. And what would make it look really nice maybe is if we took this 8 in front and distributed it through, because then it would cancel out with this 8 in the denominator in the second half. So let's do that. So let's take this and write 1 over 27, and we could write that as 80 root 10 plus 13 root 13. And again, that's because your 8 in this fraction, the numerator, when you distribute it through to the second term, it'll cancel with this 8 in the denominator. So there we have our answer. And remember, we're measuring a distance here. So this is really a measurement in terms of units, right? We don't know what the units are. Like area was units squared, volume was units cubed. This is just a distance, so it's just going to be units. Okay, let's take a look at example 2. So example 2 says find the exact length of the curve y equals the root of 2 minus x squared from 0 to 1. So if I were to quickly graph this, okay, I'm going to have, you can see this on your calculator if you put it in your calculator. Here's 1, 1, and it just kind of goes a little beyond 1. It kind of makes this arc here, and we are only interested in the portion that is going from 0 to the value of 1. So we're only really worried about this portion of the arc length. So this is the part I want to really pay attention to. Okay, now again, we're dealing with the curve. We're still, dealing with the same curve, and that curve is y equals the root. We didn't have to solve anything this time. So it's just this original function of 2 minus x squared inside the radical. And so I'm going to rewrite that to make the derivative process a little easier, and I'm going to rewrite that as a 1/2 power, and then I'll take the derivative. Now this is going to be a chain rule, so bring that 1/2 forward. The inside stays the same for a moment. Reduce your exponent, and now multiply by the derivative of the inside, which in this case is negative 2x. And then, of course, you always want to try and clean it up when you can. So this will clean up to negative x over 2 minus x squared to the 1/2. Or you can think of it as negative x times 2 minus x squared to the negative 1/2, however you prefer to see that. So what we're going to do now is use it in our arc length formula. So we are going to get that. So remember that's length is equal to the integral, and remember our integral was from 0 to 1 as given. So from 0 to 1, that's our arc. And it's the square root of 1 plus the derivative squared. And our derivative in this case is negative x times 2 minus x squared to the negative 1/2 power. And that is being squared. So our derivative is squared dx. So let's take a moment and clean that up a little bit. If I were to square negative x, that's just going to give us an x squared. Sorry, I'm getting behind here. So 1 plus, and then we'll have our x squared, because negative x times negative x is x squared. And then this piece in the parentheses, that's to the negative 1/2 power, and that's being squared, so you have power to a power there. So that's going to become 2 minus x squared to the negative 1st power. Okay, so let's take a moment and rewrite that. So some of the items are going to need to go in the denominator, and some of them will stay where they are. Okay, so looking at this, it doesn't look like, U substitution would work right away. We definitely need to maybe get a common denominator to see, if this can simplify it all. So let's go ahead and get a common denominator. So from 0 to 1, and so we'd have 2 minus x squared, and then that'd be plus the x squared in the other part. And then our denominator would just be 2 minus x squared. So we multiplied the 1 in both the numerator and the denominator here by 2 minus x squared. Okay, and that's how we got this piece right here. Okay, now the x squareds, if you look at that, they actually cancel out. Okay, and that leaves us with the integral from 0 to 1 of 2 minus 2 minus x squared dx. And so I'm going to try and simplify this into a form that I can work with. And this denominator here is starting to look like some sort of trig stuff that we worked with before, but the 2 on top is baffling me for a minute. So I'm going to take that 2 and kind of break it up. So the radical 2 over the radical of 2 minus x squared. And then I'm going to take that radical 2 in the numerator and actually going to put it in front because it is essentially a coefficient, right? So we're just going to put that in front, 0 to 1. And all we're doing here is just really manipulating things. We're just trying to get it into a form so that I can end up taking the antiderivative. All right, now this looks really familiar to something that we did in the last unit. This is looking like we have to do some trig substitution, and our denominator here is inside the radical, and this reminds me of the sine function. So that means I'm going to use this setup. Okay, oops, that should be a theta, because I already have things in terms of x, so I need to make sure I'm using a different variable when I'm doing any sort of substitution. So x is equal to a times theta, and my a value is going to be radical 2. And it's going to be radical 2 because radical 2 times radical 2, or the square root of 2 times the square root of 2, is what's giving me this 2 inside here. So square root of 2 times square root of 2 is equal to 2, so that's my a. So we have x is equal to square root of 2 sine of theta. And the dx that goes along with that would be the cosine. So radical 2 cosine of theta d theta. And remember, whenever you're doing this, you always want to try to draw that triangle to make sure that you ended up with the same square root that you started with. So here we go with our angle, and we know that the sine function is equal to x over the square root of 2 using this equation here. I just moved the square root of 2 over through division. And we know that sine is opposite over hypotenuse. So that means in this triangle that I drew, the opposite side is x, and the hypotenuse length is the square root of 2. So we just need to figure out what the length is on the bottom. And to do that, remember we use Pythagorean theorem. And so this will end up giving us that the length is equal to 2 minus x squared inside the square root. So this radical here, 2 minus x squared, is what we started with in the denominator of our integral. So I know that I'm setting up my trig stuff correctly. Okay, so now that I know I'm setting it up correctly, let's actually do the trig substitution. So we are going to have this square root on the outside. I'm going to leave off the bounds for now since we're going from x to theta. So my bounds are no longer in play for a moment. And anywhere I see an x, I'm going to plug in this 2 sine of theta, or square root of 2 sine of theta. Anywhere I see my dx, I'm going to plug in the 2, or the square root of 2 cosine of theta. Okay, so we have okay, now, so we're going to clean this up. The first thing I'm going to do is move this square root that is with the cosine out in front. I'm also going to square the inside of this denominator. So 2 squared is 2 and sine squared is sine squared. So now that we've brought that square root of 2 through up to the front and squared in the denominator, we're going to pull out the common 2 in the denominator, factor out that 2, and put the cosine up in the numerator. Now that we've done that, we can use the Pythagorean theorem identities to see that 1 minus sine squared of theta is cosine squared. And now that we've replaced that, we can separate these two into the radical 2 and then the radical of cosine squared. And the square root of cosine squared is just cosine. So in the denominator, we'll end up with just cosine with a square root of 2 in front. Now that we've simplified that, I'm going to bring the square root of 2 that's in the denominator in front with the coefficient 2. Now what's really cool is these two cosines will simplify down to 1, and we'll end up with just the integral of 1 with the coefficient 2 root 2. So 2 over root 2, 1 d theta, and we just have to take the antiderivative of 1 in terms of theta, which would just be theta. Bring your coefficient along, and we need to then put this back in terms of x so that we can evaluate our integral using our bounds from the very beginning. And to put this back in terms of x, I'm going to scroll up here to that starred equation from before. We're going to use this equation to help us solve for theta. So I'm going to divide by the square root of 2 and then take the arc sign or the inverse sign to get theta by itself. So now that I've replaced theta with the arc sine of x over the root of 2, again, using that equation we starred at the top, so dividing by the square root of 2 and taking the inverse sign, we can now evaluate. Now, I can simplify this. 2 over root 2 is really just root 2, right? Because this is to the first power and this is to the 1/2 power. And you can use your power rules there. So really, if you want to make it a little easier on yourself so that you don't have to worry about that coefficient so much, you can just evaluate it using the root of 2 in front. Now you can evaluate it at 1 and 0 and simplify. So let's go ahead and do that. So we would have radical root 2 on the outside and the inverse sign of 1 over root 2 minus arcsine of 0. Okay, now remember what the inverse sine and all mean. It's saying at what angle does sine equal 1 over root 2, or at what angle does sine equal 0? So you're looking at the inside of the sine function here, or the arcsine function, to figure out the question. So the first one is saying at what angle does the sine function equal 1 over root 2, and that is at pi over 4. So I'm going to write that down. And the second one is asking at what angle does the sine function equal 0, and that is at 0. So pi over 4 minus 0 is really what we have in there with the with the radical 2 in front. So pi over 4 timesing that would simplify to give us pi root 2 over 4. And this again is units because it is a distance measurement. Okay, so that was a pretty lengthy one because we had to use the idea of trig substitution. So all of those wonderful trig skills that you learned may pop up from here and there. So don't forget those things. But this was, again, just finding the length of the curve of the given function from 0 to 1. So remember I said you can find the arc length in terms of x, which is what we've been doing, but you can also find it in terms of y. So here we have the derivative in terms of y, but the whole process really follows the same patterns. You're going to find the derivative of your function, use that in your arc length formula, and another difference is that your A and B values, which here are listed as C and D, those are Y values from the points if you're given a point, not the X values. So those are the really main differences here. You're just working in terms of Y. Okay, so let's look at an example. So going to example 4, we need to find the exact length of the curve, and it's given to us in terms of y, and notice that our bounds are also in terms of y. So we are ready to roll. These are our boundaries, and we are in terms of y. But again, just because we're in terms of y doesn't mean that anything's really changing. It's just looking at a different variable. So here's our equation that we're starting with. Y to the 4th over 8 plus 1 over 4y to the 2nd. And I'm going to rewrite that a little bit so that it's a little easier to take the derivative of. I'm going to write that as a 1/8 in front, a y to the 4th, and then plus a 1/4 in front with a y to the negative 2. I think that'll be a little easier to take the derivative. Okay, so now that I'm going to actually find my derivative, I'm going to bring my exponents forward. So I'm going to get a 1/2 y to the 3rd and a negative 1/2 y to the negative 3rd. Okay, and that's what I'm going to plug into my formula. So I've plugged the derivative into our formula. Again, it's in terms of y, so I have a dy on the end here. And notice my bounds are in terms of y as well, 1 and 2. They were given to us, but if they were given to us in terms of points, we would just take the y values. So I forgot my squared on my derivative, so I need to make sure to have that. It's something very easy to forget. So now that I have this piece squared, I'm trying to see if I'm able to take the antiderivative yet, and I can't. So I need to try to find a way around what we currently see here. And this squared here is kind of pushing me to try to expand or FOIL out this exponent of a 2 to see what all these pieces would end up being. So let's look what that would be. So we are going to expand this out. So we're going to essentially FOIL. So take our first terms and multiply them. That would give me 1/4 y to the 6th. Then we'll do the outer terms. This would give me negative 1/4 y to the 0 power. Then we can do the inner terms. So negative 1/4 y to the 0 power again. And then our last term, which would be positive 1/4 y to the negative 6th. Then I'm going to simplify. Remember, anything to the 0th power here, so y to the 0th power is going to be 1. So these two in the middle are going to combine to give us negative a half. Okay, so what I've done here is I just combined my like terms in the middle. So I have 1/4 y to the 6th minus a half plus a 4th y to the negative 6th. And I replaced that quantity squared with its expanded form in my formula. And so now I can see that this 1 and a negative a half can combine. And so again, my integral is still pretty much the same. My bounds aren't changing because I haven't really changed variables or anything. I'm just rewriting the way it looks. So what I have here is 1/4 y to the 6th plus 1/2 plus 1/4 y to the negative 6th. Okay, so my gut reaction is that this might be something that we can factor. So let's see if we can work on the side and get it to factor. Okay, so this looks like a perfect square trinomial to me. It looks like it's in the form a squared plus 2ab plus b squared. So if I were looking at this, I have my 1/4 y to the 6th plus 1/2 plus 1/4 y to the negative 6th. Looking at this, this is kind of showing me, okay, well, 1/2 y to the 3rd, that's my a, and 1/2 y to the negative 3rd, that's my b. And so you can kind of see that in our formula here, that if I were to multiply these two together and multiply by 2, so 1/2 times a half is a 4th times 2 would give me a half. And then y to the 3rd times y to the negative 3rd would give you y to the 0th. So that middle term is certainly following this pattern here that we have this 2 times ab. So this 1/2 does result from the multiplication of the a and b here. We definitely have a perfect square trinomial. So we can actually write this as 1/2 y cubed plus 1/2 y to the negative 3. 1/2 y cubed plus 1/2 y to the negative 3. So you can write that as a power of 2, since they're the same factor twice. And what that will allow us to do is get rid of our square root over here on the left. So I'm going to take this form, this factored form, and replace this long expanded form with this now simple factored form. Okay, so I have taken this factored form and replaced our expanded version with our factored form. And because it's just the square root of something squared, we're left with just the insides. So now we can go ahead and write this as the integral from 1 to 2 of 1/2 y to the 3rd plus 1/2 y to the negative 3rd. And I just realized that when I wrote the above part, I put a y there instead of a 2. So let me go ahead and fix that. Okay, so now that we kind of have this rewritten, now we can take the antiderivative using our general old school antiderivative rules of add 1 to your exponent, divide by your new exponent. So we're going to have the half in front, and then this is going to be y to the 4th, and we're going to get a 1/4 in front, plus 1/2 times, and this is y to the, now we're adding 1 to negative 2, so that's going to become a negative 2, so we're dividing by a negative 2, so in other words, multiplying by a negative a half. And then we're evaluating this. We've never changed variables, so our bounds have always stayed as 1 and 2. So let's simplify this a little bit. That's going to give us 1/8 y to the 4th minus 1/4 times 1 over y squared. And now we're going to evaluate that at 2 and 1. So I've taken the 2 and plugged it in, and then I'm subtracting the evaluation at 1, and now we can simplify this. So this will give us 2 minus 1/16 minus 1/8 plus 1/4, and that is including the distribution of that negative in front of the parentheses right here. And now we just need to combine all those into a common denominator and get a fraction that works. So after doing so, we get 32/16 minus 1/16 minus 2/16 plus 4/16, and together that is going to give us 33/16 and again, those are units because it is some sort of distance. So there's the arc length for the given situation. And again, this was in terms of y, but notice the process was exactly the same. We were just working in a different variable. Now this one was interesting because we did need to expand it and then find that perfect square in there. So sometimes you will have to do a bit of algebra work in order to get it so that your integral simplifies nicely. All right, so here's the last one for the video. We can get through this, don't worry. But of course, I left the doozy for the last one. This one is in terms of x. Y is equal to the ln of 1 minus x squared. We're going from 0 to 1/5, and we're trying to find the exact length. So our original function is just going to be y is equal to the ln of 1 minus x squared. And we need to find the derivative of that, so let's find it. So remember, it's 1 over the inside when you're dealing with the ln function. And since there's more stuff going on the inside, we have a bit of a chain rule, so that's going to be times negative 2x. So that would simplify to give us negative 2x over 1 minus x squared. So there's our derivative. So let's start putting this into our function, or our formula for length. So we're going to go from the integral from 0 to 1/5. And remember, it's the square root of 1 plus the derivative of the function, so negative 2x over 1 minus x squared dx. So before we go too far, I'm going to take a moment and expand out this piece that's to the second power. So I'm going to expand it out and actually take negative 2x over 1 minus x squared to the second power. So when we do that, it would become 4x squared in the numerator, and the denominator would become 1 minus 2x squared plus x to the 4th. And I'm going to rewrite that so that it's large exponent in front. So now my denominator is x to the 4th minus 2x squared plus 1. So I'm going to take that and replace that quantity squared in the radical as the expanded form. So now I have 1 plus 4x squared over x to the 4th minus 2x squared plus 1 in the radical. Now I have this 1 on the left here, and I'm going to get a common denominator. So remember, if it's just a 1, the denominator of the other piece, the fraction on the right, this x to the 4th minus 2x squared plus 1, that's just going to be the same thing in the numerator and the denominator. So I'm just going to go ahead and rewrite that as a common denominator. So as you can see, this denominator was just replacing the 1, so the numerator and the denominator are the same. So this would be 1 plus our other half here. So here we have a new common denominator combined fraction, and we're going to take a moment and combine those like terms of negative 2x squared and positive 4x squared. So now we have a nice polynomial in our numerator and a polynomial in our denominator. So I'm going to see if anything might be able to cancel out. So if I take a moment and try and factor the numerator and factor the denominator separately, I might find that there are some common terms that could cancel. Okay, so what I did is I just wrote the numerator over on the side and the denominator over on the side so that I can take a moment and try and see if they simplify at all. So the first one would simplify. I would get x squared plus 1 and x squared plus 1, which can be rewritten as x squared plus 1 to the second power. So that's my numerator. My denominator would simplify very much in the same way, only with the opposite sign. So we have x squared minus 1 and x squared minus 1. So we have x squared minus 1 to the second power. So I'm going to take a moment and rewrite my square root on the left, that's inside the integrand, using these factored forms. And by having these factored forms, notice they have an exponent of a 2, both of them, so that will be able to simplify with the square root, and that will help us get this out of the square root. Okay, so nothing canceled out in terms of factoring and simplifying a factor, but we did make it so that we are able to get rid of that square root. So now that I see these new polynomials here in factored form, the square and the square root for both of them will cancel, and I'll be left with just what's on the inside. So now I'm going to have the integrand from 0 to 1/5 of, no longer will I have a radical. I started to write it because I think I'm so accustomed to writing it, but no longer will I have that radical. And now I'll just have x squared plus 1 over x squared minus 1. Now, the sad truth is that this can't be done with an integral using like u substitution or any of the simple ways that we know until we start to do, you guessed it, partial fraction decomposition. So we have to employ the idea of breaking this down into fractions, and we also have to break this down, in this particular case, using long division, because our exponents of both our numerator and the denominator are equal. So we need to do long division first, so that then we can use partial fraction decomposition to take the integral and then finally find our answer. So this is a very involved question. All right, so I'm going to set up the long division piece first. Okay, so I've set up the long division. Don't forget you need placeholders for any of the terms that you're missing. So you need a 0x for both of them. And then you just need to look at what's inside your division bar, and you need to say, okay, I have an x squared on the outside. What times x squared will give me what I have on the inside? And the answer is just a 1. So I'll put a 1 there. And then you take that 1 and multiply it through by your divisor. So 1 times x squared is x squared. 1 times 0x is 0x. And you know what I realized? This is supposed to be a minus. The divisor is what's in our denominator here, and our divisor is a negative. So I miswrote that. So let me put a negative there. Okay. So we started with 1 times x squared is x squared. 1 times 0x is 0x, and 1 times negative 1 would be negative 1. And remember, we are subtracting these guys. So our x squared and x squared terms should cancel, which they do. X squared minus x squared is 0. 0x minus 0x is 0, but 1 minus a negative 1 is 2. So I have a remainder of 2. And when you have a remainder, you write that remainder over your divisor. So that is how we're going to break apart the first part of this partial fraction decomposition. So let's rewrite this integrand using this long division piece. Okay, so we have the integral from 0 to 1/2 of 1 plus 2 over x squared minus 1 dx. Okay, but this x squared minus 1, that can be broken up. So we actually have to do a partial fraction decomposition on that. And that's where the partial fraction decomposition comes in. So I'm going to break this up into 2. I wrote that as a 1/2. That should be 1/5 for our bounds there. So 1/5, there we go. All right, so we have 1 as our first integral, and then our second integral is going to be this 2 over x squared minus 1 dx. Okay, now, so let's do the partial fraction decomposition on this one. Now remember, my denominator can factor into two terms here. I would have x minus 1 and x plus 1. So that's how I'm going to break apart the two fractions that I have for my partial fraction decomposition. So one of them is going to be x minus 1, and one of them is going to be x plus 1. And I will have an a and a b. And again, you're having an a and a b because my factors are linear, so I need constants for my numerators. Okay, now I'm going to multiply through. So remember, the denominator is what we're multiplying through by in factored form. So that's going to leave me with a 2 equal to, and remember, a will multiply with the factor that's not its denominator, because its denominator would cancel when it multiplied through. So we would have x plus 1 plus b x minus 1. Okay, so we're doing our partial fraction decomposition, and we can do the shortcut on this one if we let x equal 1 using the idea of what numbers would equal our factors. If we let x equals 1 on this one, 2 would equal a times 1 plus 1 plus b times 1 minus 1. That 1 minus 1 would go to 0, and we would end up with 2a is equal to a, which is telling us that a is equal to 1. If we did the same idea to figure out what b is, let x equals negative 1, we could say, okay, well, 2 is equal to a times negative 1 plus 1 plus b times negative 1 minus 1. The negative 1 plus 1 would go to 0, and we would end up with negative 2b is equal to 2. And so that would tell us that b is equal to negative 1. So we now know what our a and b values are, so we need to do our antiderivative. Setting up those fractions just real quick ahead of time, our a number was 1, so that's going to be 1 over x minus 1, plus our b value, which was negative 1 over x plus 1. Okay, so now I'm going to take a moment and rewrite these integrals over here to see if we can find their answers. Okay, so I took our two partial fractions here that we decomposed, and we have now rewritten this 2 over x squared minus 1 into these two integrals with separate fractions for each. And I just took the negative from this coefficient or from that numerator and put it out in front. Okay, so notice all my bounds are still from 0 to 1/5 because I'm still in terms of x. That has not changed. All I did was separate each of the pieces into its own separate integral to help make doing the integration easier. Okay, so what I'm going to do for these two, the last two integrals, I'm going to do a quick u substitution. So my u in the first one is going to be x minus 1. My du is going to be dx. So really this is just the integral of 1 over u. And if I were to do the same thing for the other one, it's going to be x plus 1. dw is equal to dx. And so really this is just the integral of 1 over w dw. Okay, so this is just a real quick answer of an ln there. Nothing fancy when we write our final answer. So now let's take the antiderivative. So the antiderivative of 1 in terms of dx is just an x. So this first integral is an x plus the second one is just going to be the ln of the absolute value of u, which in this case is x minus 1, plus this third one is going to be, a negative, so it's a minus sign. So it's a minus, and then the ln of the absolute value of w, and w is x plus 1. Okay, so it's not going to be a plus c because we're trying to evaluate this at 1/5 and 0. So take a moment and plug 1/5 into this. Okay, so we have replaced all of the x's with 1/5 and then replaced all of the x's with 0. Now this whole back right-hand side, 0 plus the ln of the absolute value of negative 1. Well, the ln of the absolute value of negative 1 is the same as the ln of of 1, which is just 0, and the second part here is also just the ln of 1, which is 0. So this whole entire backside just cancels out to 0. So I just need to worry about this first part. Here we have 1/5 plus, this would become the ln of 4/5 using the absolute value idea, minus the ln of, 6/5. Started to write the absolute value bars, but we don't need those anymore. So 6/5, and using the properties of logs, I can combine these two ln functions into one. So I could write 1/5 plus the ln of 4/5 up top over 6/5 in the denominator. Because of that minus, it's telling us it's division there, and then the 5s would actually end up canceling. So I would end up with 1/5 plus the ln of 4/6, which of course would reduce to 1/5 plus the ln of 2/3. And that is in terms of units, and that would be our final answer, 1/5 plus the ln of 2/3 units. That was a long problem. We did it together because of that reason. We not only had to use the idea of expansion, we had to use the idea of factoring, we had to use the idea of partial fraction decomposition with long division. Again, we had to do the long division because our exponents were equal, so we had to break it down using long division. Then the second piece, the remainder there, was broken down using partial fraction decomposition, where we had to factor our denominator, solve for a and b. Once we were able to do that, we were able to get our separate little integrals, and some of them we had to use u or w substitution. But once we did that, we were able to get everything back in terms of x and evaluate it at our original upper and lower bounds, giving us 1/5 plus the ln of 2/3 units. So that is the video for arc length. Remember, we are this entire time just finding various lengths of arcs, of curves. So we will learn more about this in class, about finding the actual arc length function.